periodic table shows the chemical elements according to their abundance and availability on our planet. Hydrogen is the most simple element that exists, composed only of a proton and an electron. It is the most abundant in the universe and the third most abundant on our planet. In its molecular form, composed of 2 hydrogen atoms, it is a colorless gas, which cannot be perceived by smell or taste. It is 14 times lighter than air. It does not, of course, contain carbon, and it is not toxic, irritant, or corrosive. Being the most abundant element in the universe, hydrogen is rarely found in isolation. It is almost always combined, forming part of other substances such as water, hydrocarbons, cellulose, and so on. The simplest molecule is H2, that is, 2 hydrogen atoms that share their pair of electrons. Hydrogen is present in simple inorganic molecules such as water when combined with oxygen, and ammonia, in which 3 hydrogen atoms are combined with 1 nitrogen atom. It is also present in hydrocarbon chains, such as methane, or C1 because it contains a carbon atom, ethane, C2, propane, butane, etc. And of course, it's present in other organic molecules such as fatty acids. An organic compound is considered unsaturated if it contains a double or triple bond between some of its carbon atoms. Let's see some significant reactions. Starting with the decomposition of water into hydrogen and oxygen, it is important to understand that this is an endothermic process. That is, it requires an input of energy for this dissociation to occur. In the opposite direction, the association of hydrogen and oxygen produces water and releases energy. In electrolysis, for example, electrical energy is supplied to produce hydrogen and oxygen. At the other extreme, a fuel cell will be fed with hydrogen and oxygen from the air, producing electricity and emitting water. Taking, for example, the ammonia molecule, widely used as a hydrogen carrier, we see that its dissociation is also endothermic. That is, it requires an external energy supply to separate it into nitrogen and hydrogen. Finally, we see a widely used process to produce hydrogen from methane. It is called steam methane reforming, SMR. In the presence of a catalyst, methane reacts with a stream of pressurized water vapor, producing carbon monoxide and pure hydrogen. The first reaction is followed by a process called water-gas shift reaction, which allows the monoxide to react with water to obtain more hydrogen and to avoid the release of the carbon monoxide. The final result is hydrogen and carbon dioxide, the latter being a greenhouse gas, which should be captured to minimize environmental impact. We'll see this subject when talking about the colors of hydrogen. A very important concept when comparing different options is energy density. How much energy does a kilogram of the product contain? We call this gravimetric density, and it is measured in megajoules or kilowatt-hours per kilogram. How much energy does 1 liter of the product contain? This is the volumetric density, expressed in megajoules or kilowatt-hours per liter. This diagram represents the energy densities of different products. An initial conclusion we can draw is that hydrogen has the most gravimetric density. 1 kilogram of hydrogen contains more energy than 1 kilogram of any of the other fuels. On the contrary, its volumetric energy density tends to be lower than many of its competitors, requiring more volume to store the same amount of energy. It's evident that, in a gaseous state, the higher the storage pressure, the higher the volumetric density of hydrogen will be, as can be seen in comparison between 350 and 700 bar. On the other hand, liquid hydrogen at a temperature of minus 253 degrees C has even more volumetric density than in the gaseous state. The question arises, if hydrogen is supposedly worse than other fuels in terms of volumetric density, why use it? Let's remember, hydrogen is the cleanest fuel. Its combustion releases only water since it does not contain carbon. We will return to this concept of energy density when discussing storage and transportation methods. Going deeper into the question of how much energy is contained in 1 kilogram of hydrogen, we find that there are two ways to measure the amount of heat/energy that will be released when combustion occurs. Higher heating value will consider all the energy released in the combustion, including the one that is delivered when the resulting products reach the starting temperature. Lower heating value treats the products in the gas phase. It does not consider the energy necessary to vaporize the water. An electrolyzer which produces hydrogen from water and electricity will have to be supplied with more than 39.4 kilowatt hours of electrical energy to produce 1 kilo of hydrogen. The efficiency of the electrolyzer is usually measured in relation to the higher heating value. If, for example, an electrolyzer requires 50 kilowatt hours per kilo of H2 produced, its efficiency would be 39.4 out of 50 for a total of 79%. On the other hand, the efficiency of the fuel cell, which consumes H2 and produces electricity and eventually heat, will be established using the lower heating value as a point of comparison.